or why zero emission vehicles may not be a panacea for reducing criteria pollutants. I will let Gary take the helm and start the presentation.
There we go. All right. Well, thank you, everybody. Thank you for inviting me. Thank all of you for joining today. I hope I'll make the time you're committing here worthwhile. And I'll start out by making some brief acknowledgments. It's hard to acknowledge everybody, but the instrument that has collected all the measurements that I'm going to talk about today was the brainchild of my boss for 30 years, Dr. Donald Stedman. He had the idea back in the mid 70s, but it took him almost 10 years before he could convince anyone to fund it. And that lucky agency turned out to be the Colorado Office of Energy Conservation. And the funny story behind that is they actually rejected the proposal the first time that it was reviewed. They told Don that it had been rejected, and so he moved on to something else. And a couple of months later, they got some additional funding money, and instead of asking for new proposals, they went back through the ones they had rejected and ended up calling him and telling him that they had funded this project out of the blue. And so he had to get things going fairly quickly after that point. But this all started in 1987. I'll acknowledge that the Coordinating Research Council, who probably many of you have never heard of before, it's a research umbrella organization for oil and refiners and automobile manufacturers. They have funded a number of the data sets that you'll see today and have supported regular measurements, especially on light duty vehicles, for more than 25 years. So they're one of the big things. And then while it is a one-man operation today, over the past 34 years, they've been lots of students and postdocs and visiting professors and a host of others that have contributed to the data that I'll show you today. It's not just my work. Let's see, next slide. There we go. So this is a picture of the instrument that got nicknamed the Fuel Efficiency Automobile Test, or short, we just call it FEAT. This is the most current version of the instrument. This is a picture taken on a ramp in Chicago. And it's composed of a light source, a series of detectors that operate in both the infrared and the ultraviolet wavelength regions. We use usually single lane roads, though it is possible to do multi-lane environments. Typically, we just set up on single lane environments. In addition to making tailpipe exhaust measurements, the device also captures speed and acceleration. We take a picture of the license plate of the vehicle and we acquire non-personal information from registration statistics to be able to put with the emissions measurements so that we can do the analysis and the statistics that we want. FEAT is basically an open path absorption spectroscopy. And I'm sure many of you in high school or college worked with a desktop spectrometer. It had a light source, a detector, some type of sample cell. Usually it was just a cuvette. You put a liquid in, you stuck it in. There was some type of wavelength selector, and you were able to correlate the absorption measurements to the concentration in the sample by knowing the path length of the sample. And so one of the technical barriers that Don had to overcome when he envisioned building FEAT was this idea that when we set up across a single lane road, basically we've cut this spectrometer in half. We put the light source on one side, we put the detectors on the other. But the problem is that while we can measure the absorption in that path length, we never ever know the path length of the gases that we're measuring. And so from the Beer-Lambert equation, that presents a problem because without the path length, you can't relate the concentration of the absorbance. And the brilliant idea that Don had was that you did not have to measure a single species, and that you could measure everything and ratio it to carbon dioxide, which is the primary pollutant in a tailpipe. And now when you measure a ratio behind the car, you have both a numerator and a denominator with a Beer-Lambert equation, one for CO, for example, one for CO2. Because the exhaust is coming from a single point, the path length in both of those species for the absorption measurements that you're making are the same, and they cancel out. And all of a sudden now path length is not an issue. And so feet actually measures molar ratios of each pollutant to CO2. So let me just give you an idea of how we go about doing this. So in this top graph, this is a half a second of data collected at 100 hertz behind a vehicle. And you'll notice that I've plotted CO2, CO, and hydrocarbons. I've got time on the x-axis, and I've got concentration on the y-axis. And you'll notice that they're all bouncing around and they're moving together. This is a very high emitting CO and HC car, and I've chosen this on purpose just so that you can see the fact that the lines move together. Now we ratio both CO or HC individually to this CO2. And if we have a single plume from a single point source, that ratio should create a correlation graph that's linear. And you'll notice down to the left, in the bottom, there's a correlation graph for CO versus CO2 on the left, and there's a correlation graph for HC versus CO2. We fit a linear least squares line to that correlation, and the slope of that line is the molar ratio for that species that we've measured. The steeper the line, the larger the molar ratio, the more CO or hydrocarbons that's coming out of the tailpipe of the car. And for this vehicle, these are very large numbers. Is there a way to get rid of this hang up bar and stuff? I can't see the slide. Anyway, so for a car that has no CO or CO2, you'll have a slope of 0 and a flat line. And this brings up another thing that you'll see in today. You will see negative molar ratios in a number of the slides that I show you today. Now, we can take the molar ratios and convert them into fuel-specific emissions. It's just a straightforward thing, and we'll end up with grams of CO or grams of hydrocarbon per kilogram of fuel burn. But for a 0 measurement, as I mentioned before, we're going to end up with a line that has a slope of 0. But because our instrument has noise inherently built into the measuring process, the environment that we're operating in can produce noise, there will be a normal distribution of measurements about 0. And we'll end up with slopes that are slightly positive for a 0 measurement, like you see in the top graph here, where we've got HC versus CO2, or we can end up with ratios where the slope is slightly negative, as we see in the bottom part of the graph. A negative ratio doesn't mean the car is cleaning the air. It's just a measurement of 0 with some amount of noise that we have to deal with. And so this normal distribution of positive and negative numbers around 0 produces a 0 reading when you have a statistically significant enough number of samples. And so we leave the negative ratios in because while they are just a measure of 0, there's also a positive value of similar magnitude that is also 0 and not really negative. And if we were to throw the negatives away or turn them into 0, we end up biasing the measurements high. So you will see negative values in a lot of the plots that I show you today, and this is the source of those negative values and why we leave them in. Now, we've measured lots of things other than just light-duty cars and trucks. That'll be the focus today, light-duty cars and trucks. But I just thought I'd introduce you to the fact that we've made measurements on basically all types of vehicles all across the U.S. and around the world. This is just a few of the examples. One of Don's students has even measured cruise ships and container vessels off of a bridge in Vancouver. Quite a feat just by setting the instrument up on top of the bridge. And then I included this slide, not so much that I'm going to go over it or show you that we've made lots and lots of measurements, to point out the website that's listed here at the bottom. All the data sets that I'll show you today, all the data sets that we've ever collected, all of our journal articles, all of our reports, a lot of our presentations, this, that, and the other. You can find all of those at this website. So if there's some idea that you've got, you didn't like the graph I made with a certain data set, you think it should have been sliced up another way, you can go to the website here, you can download the data set and you can have at it. And a lot of people have. Maybe one of the more important things we did was create this data repository. At least in the last decade, there have been 10 to 15 other researchers that have used the data off of this website in their own research and in their own publications. And so it has become an important source, at least for in-use emission measurements. So why are we talking about light-duty vehicles and emissions and criteria pollutants? Well, by and large, in Denver today, the issue behind light-duty cars and trucks and their emissions has to do with ozone in the area. And this is a historical plot that I put together, finding data from the Colorado Department of Public Health and Environment, that shows the fourth high max for the 8-hour average ozone in parts per billion versus year, going back to 1992. And what you'll notice right off the bat is that the two high readings in 1998 and 2002 draw your eye in and make you feel like that things have gotten better in the last 20 years since then. And it looks like things have gone down. But if you'll try to block out those two high readings and just look at all the other readings in the early 90s that are around them, what you basically see is that for the last almost 30 years, the fourth high max ozone in Denver has wiggled around the 80 ppb line, and it hasn't moved up or down in any significant way. In hot, dry years, we tend to move above 80 ppb like we did last summer. And in cooler, wetter years, we tend to wiggle below the 80 ppb line. But by and large, it hasn't changed in almost 30 years in terms of the fourth high max. Now, the fourth high max is an extreme statistic, but it is the statistic prior to 2008 that was used to measure compliance. Since 2008, they have what they call the design value, which is all it is the fourth high max averaged over the trailing 3 years. And so you end up with some smoothing in the design value and readings, and the highs and the lows are minimized to some extent, but they don't change this picture. And what's fascinating about this picture is that I don't know the age demographics in my group that's listening today, but over this time period, there have been some seismic changes in the emissions inventory and other things in Denver. Think about this for a while. CO and HC emissions have probably been decreased more than an order of magnitude, maybe even a factor of 20 in some areas over this time period. Population along the Front Range has probably, it's close to doubling over this time period. That would double the amount of cars that are on the road, probably the amount of miles traveled, the amount of fuel that's being used. We've closed multiple coal-fired power plants during this period. We've also opened gas-fired power plants. There's been probably at least 2, if not 3, boom and bust cycles for the oil and gas industry. And all of those changes, many of them huge, hasn't moved the fourth high max ozone in Denver for these 4 sites. Now, these are the 4 sites where it typically records the highest readings. There may be some others that will occasionally violate the standards. The other thing that I always think that's funny that I like to tell people, so the American Lung Association has a publication they release every year called The State of the Air. And it started in 2000, and they've done it every year since then. In 2000, Denver was on the clean air list. But now we regularly make the, if not the Dirty Dozen, the top 15 in terms of their list, in terms of unhealthful air. And the only thing that's really changed is the standard of what we decide is healthful air, because the air hasn't changed. It's pretty much the same as it was for ozone back in 2000. But I always think that's curious. So we've gone from a standard of 100 ppb in 2000 to 70 ppb today. And so you can see the change in terms of how Denver is ranked in terms of air quality. So I thought I would just go back and show you some of the data that we've collected over the years and talk about its implications. So this is a graph of all of the data sets that we've collected in and around the Denver area since we started collecting sets in 1989. And as I mentioned before, CO emissions have come down dramatically. These are fleet averages that includes gas and diesel vehicles, everything that went by at the sites that we were working at. Basically, since 1999, the majority of these points are from a 6th Avenue and I-25 site, though there are a couple in the early 2000s from a Spear Boulevard site that doesn't exist now. But you get the general idea. I mean, we've gone from about 120 grams of CO per kilogram of fuel down to 5. You see a similar pattern for HC and NO. You'll notice that we don't go back as far with each of these pollutants, and that has to do with changes that we made to the instrument over time as we added the ability to measure new species. We started out with CO, and then we added hydrocarbons, and then we added NO. NOs, we've been measuring the shortest amount of time, and it's probably decreased the least. It's probably gone down by maybe 60% in this graph, 65% since 1999. But all of these show a similar trend, kind of an exponential decay as they approach zero for all three of these species. Now, the other thing that's changed dramatically over this 30-year period is the age of the fleet that's on the road. This is a graph of the fleet percentage from the 6th and I-25 site, looking at data sets that we collected in 1996, when the average age of that fleet was 7.2 years old. And the last data set that I collected there, which was January and February of 2020, right before the shutdowns happened. And what you'll notice is that in 2020, the fleet age is about 1.6 years older than it was in 1996. Now, it turns out in 2018 at this location, the fleet age was 9.2 years. And my guess is if I went back out there today, the pandemic, which has increased fleet ages in other cities that I've measured since the pandemic started, probably has pushed this back up to about 9 years old again, or 9.2. And so in general, the fleet today on the road in Denver is 2 years older than it was 25 years ago. The 2008 recession is the big reason for that. And you can see that drop there. There's kind of an inflection point that marks the 2008 recession. And since that, 2008 and newer model years are not 2000, yeah, 2009 in newer model years are in have less frequency in the fleet than what we saw 20 years ago. And that as you go back 12 years and older cars have more representation in the fleet today than they used to. So even with all these dramatic drops in emissions, we've seen an increase in the age of the fleet. And in the past, those two weren't compatible with one another. So what's the big deal about the emissions distribution? Well, most of us, when we think about distributions or we talk about statistics, we've mostly been exposed to normal distributions, the bell-shaped curve. When you had your score curved in high school or college on a test or whatever, the teacher used normal statistics to figure out what the mean was and what the standard deviation was and how to do that adjustment. Well, with many environmental statistics and even many other statistics, they are far from being normally distributed. In fact, most of the time they're either gamma or a log normal distribution. And because of that, things that we take for granted in normal distributions don't apply to them. For example, we're used to thinking in normal distributions that the most common measurement in that distribution, the median, is also very close to the mean. And in a normal distribution, they're always fairly close together. But in a gamma or a log normal distribution, that's far from the truth. And typically the median is multiple factors lower than the mean is in that distribution. And it has to do with the fact that the distribution is skewed, where there's an inordinate number of very small numbers in the distribution and a very small number of large numbers in the distribution. And you end up with this large tail. And so, for example, in this 2020 Denver data set that you can see that I've plotted here, and note that I've split the axis so that you get some idea that there are some numbers out there at 500 and 600 and 700 and 800 and 900 grams of CO per kilogram of fuel. I just took the 200 grams per kilogram of fuel spanned between the arrows there. There's only 115 measurements out of the 19,900 measurements that are 200 grams of CO per kilogram of fuel or more. It's 0.6% of the measurements, but it's 41% of the total CO. And it's that skewed statistic that's important when you start thinking about do we reduce criteria pollutants in a fleet, or how do we reduce them in an inventory? And you have to keep this in mind. And I'm having a hard time reading it. I want to say the 99th percentile, just for X, is at 147 grams of CO per kilogram of fuel, just to give you a normal, whereas the mean is 4.7. So 1% of the cars are above 147, and the median is at 0, which is half the cars. This is another way to look at the differences and the changes over that time. So going back to this 6th and I-25 site, and I've graphed the 1995 and 96 data set that we collected there. We've been collecting wintertime measurements in December, January, and February at this site since 1995. And so that's why I'm using it. And I've plotted fuel-specific CO emissions versus age for these two data sets. Now, keep in mind, we're comparing apples and oranges here in terms of vehicle technologies, but I've at least shown you what 1-year-old cars and 5-year-old cars and 10-year-old cars look like in terms of a comparison. Because if I graphed them on a model year basis, they would be at one end of the graph and the other, and it'd be hard to do the comparison. But what you'll notice, of course, is that in 1995 and 96, while brand new 0-year cars had very low CO emissions, they started increasing almost instantly as you went backwards. And they went to a very high level and then leveled out around 250 grams per kilogram. In contrast, in the 2020 data set, they hardly rise off the 0 line for at least the first 14 or 15 model years. And probably if you were to take 95% confidence intervals into account, the uncertainties I plotted here are standard errors of the mean. You probably go back 15, 16 years before you would get a significant difference in terms of increases on a fleet average for a model year. And so cars not only start out clean today, on a fleet average basis, they stay that way for a very long period of time. And those of you in the audience that might be old enough, as I am, you might remember, when I was getting my driver's license driving, if a car lasted 100,000 miles, it was fabulous. We were doing something right, because they just did not last that long. And now if a car doesn't go 250,000 miles, some people think they've, been gypped. And so cars start out clean today. They have a very low breakage rate, and they stay that way for long periods of time. And I can show you the same plot for hydrocarbons. And for hydrocarbons, it goes back even farther. Within the uncertainty, because I'm losing data at the end, you might could say that HC emissions are pretty much static on a model year average basis for the first 20 model years now. And a lot of that has to do with the longevity of three-way catalytic converters. I'm not showing any of that data today, but I have whole data sets of ammonia emissions from in-use cars. And one of the advantages with ammonia is that you can look at catalyst function, because a gasoline vehicle cannot produce ammonia without a functioning catalyst. And what we see today in ammonia emissions is that they will continue to be present back to between 20 and 25-year-old vehicles before they start to disappear, indicating that the catalysts are wearing out. So many three-way catalysts in our cars today are lasting well beyond 20 years. And that is good news for hydrocarbons emissions, because that's the main defense in scavenging any unburned fuel that's coming out of the engine. NOx emissions, on the other hand, do not stay down as long as we see for CO and HC yet. And a lot of that has to do with the fact that NO emissions were one of the last criteria pollutants that were tackled in the EPA regulations for tailpipe emissions. And it was really tackled starting in 2009 when they introduced Tier 2 vehicles. And the main focus of the controls for Tier 2 vehicles were on NO emissions. And what you'll notice is that 2009 model year is right around an 11-year-old vehicle. And what you'll notice is that starting around that period of time, even make back another year, we see very low NOx emissions after that period of time, much like we've seen for CO and hydrocarbons. And again, back in 95 and 96, the NO emissions went up very quickly and they leveled off at a much higher level. Another way you can look at this is data from the Chicago area that's over a similar time period. And I didn't have time to try to reproduce this from Denver, but this is a special plot. And it was kind of fortuitous. Data is collected here in two different locations. In 1992, we were at a Central Avenue location just west of downtown Chicago on I-290. And then in 2002 and 2016, we were out in the northwest suburbs at a site on Algonquin Road. What's unique about these data sets is I've got 3 control classes for tailpipe emissions. Tier 0, which basically was the pre-control vehicles. Tier 1 vehicles, which were first introduced in 1996 and ran through 2003. And then there's the gaps have to do with transition periods between the tiers when they phase another. And then Tier 2, which started with 2009 model year vehicles. All of the box and whisker plots that I've plotted here are the same age vehicles collected at different times. So for Tier 2 vehicles, we have age 1 through 8-year-old vehicles. Tier 1, they go 1 to 7-year-old vehicles. And then Tier 0, they go 1 to 8-year-old vehicles. And it's a standard box and whisker plot. The whiskers span the 10th to the 90th percentiles. The box goes from the 25th to the 75th. The horizontal lines, the median, the means plotted in there. But what you'll notice is that HC emissions tend to bottom out first. You can see with the 1996 model year vehicles in Tier 1 that are introduced, the 7-year-old vehicles, we see pretty much static distribution of HC from there going forward. You'll notice for CO that it still curves in a little bit during Tier 1, but by the time we get to the 2003 and 2002 model year cars, CO seems to have bottomed out. And then in Tier 2, it's actually slightly lower, but you'll notice it's very consistent. We go down and we look at NOx. Again, I don't have NO emissions from the 92 measurements, but you'll notice much larger spread in terms of the distributions for each of the model years in NO. And then with the introduction of 2009 model year cars going forward, NO emissions are locked in the Tier 2. Another way you can look at the differences and the changes that have happened over the time is by actually directly comparing the distributions. Now, I'm sure many of you have not seen plots like this, and it takes a little bit to get used to. So this is a cumulative probability plot. And the way you read this is you say, what's the probability of finding a car that emits 600 grams of CO per kilogram of fuel? Well, you find the 600 grams on the y-axis and you move that line across until you run into it. And then you go down and you see what the probability is. Now, the x-axis, I've actually transformed this axis so that it's a normal distribution. If the data were normally distributed, we would end up with a diagonal straight line. You'll notice, of course, it's not normally distributed, and we don't end up with diagonally straight lines. We end up with sigmoidally straight lines. And depending on the year we're looking at, that S curve happens either earlier or later. And you can see the differences that I showed in the earlier graphs on the emissions distribution. The 2020 data, you'll notice, stays on the zero line much longer than the 95 or 96 data does. And by and large, 90% of the cars in 2020 have near zero emissions for CO. You'll notice they still go up, large changes even in the 99th percentile. And as you get to the very end of the distribution, they're much closer together, but still we see significantly lower emissions even in the very extreme tails. A similar picture for hydrocarbons, though exaggerated even more. For hydrocarbons, you might be able to say we're out to 95% of the fleet that have near zero emissions in 2020. Now, high hydrocarbon emissions by and large are produced by misfires. And so typically a misfire is going to have similar emissions levels provided there's no excess oxygen for the catalytic converter to keep it down. If it's bad enough, we end up with HC levels you see at the very end there that are very similar between the two model years. And for NO, like we had in the graphs before, you see there's a much larger difference in terms of the changes in the emission distributions between 95 and 96. 2020, we've got a large percentage of the fleet are tier 2 vehicles. I want to say off the top of my head, it's 70%. 70% of the cars in the 2020 data set are 2009 or newer. And you'll notice that by and large, 90, 91% of the fleet for NO has near zero emissions. What can we do with this information and how do we look at it and what do we think about in terms of, well, where are the criteria pollutants coming from today? So I've taken the data from 2020 and I've taken the grams per kilogram of fuel emissions and I've multiplied it with the fleet frequency by model year for each of these categories. We sum up the totals. We take each model year, we sum up the totals, divide it among the different classes of vehicles. So I've plotted here all diesel vehicles. This includes cars and trucks, gasoline trucks, and gasoline passenger vehicles. And I've plotted their percent contribution to the total. And what you'll notice, I've also plotted the fleet percentage. And the open circle there is the median age of the fleet, which is about 8 years at this site in 2020. And what you'll notice that for carbon monoxide emissions, that contribution peak happens about 16-year-old vehicles. And then it starts to go down from there. And you'll see that by and large for CO, it's kind of evenly split between gas cars and gas trucks. And diesels really aren't a factor for CO. The HC contributions look quite different. If you remember that graph that was very flat in terms of the average emissions by model year for hydrocarbon emissions, it didn't change for about 20 years. And so what drives the contribution in the hydrocarbon graph now is not the emissions from the model years, but it's the fleet contribution or the fleet percentage. And what you'll notice if you look, Carrie, by and large, this percent contribution graph follows the shape of the fleet distribution. And that's what dictates where the emissions are. And you'll notice there, tier 2 vehicles are a large percentage of a small total for hydrocarbon emissions. NO emissions, in terms of their age contribution, look more like CO. We're back again to 15, 16-year-old vehicles being the part for the largest contribution. But here you can see the diesel influence. The diesel contribution at this ramp, there's only about 3% of the fleet have low exhaust in their diesel vehicles, both light and medium duty vehicles, and a few cars. There aren't as many cars now that the Volkswagens are off the road. But that 3% is about 25% of the NOx emissions. And you'll also notice that the gas trucks have a significant larger contribution than, say, the gas passenger vehicles. But here again, tier 2 and newer, 70% of the fleet, but it's only 22% of the NO of the NOx emissions. So large contribution of vehicles from these newer cars, but they have a very small contribution to the total. And I'm going to stop with this one and ask just a few questions because I think this is really going to be fascinating to look at in the years ahead. Last year, Tesla dominated sales for battery electric vehicles in the US, and they have for all the years previously. And so right now, there's really only one manufacturer that's developed some marketing buzz or some cachet, if you will, that have people excited about buying their cars. And just to give you an example of the difficulty for some of the other manufacturers, Nissan's been selling the Leaf for 10 years and they still haven't gotten to 200,000 vehicles. You can still get a federal emissions credit on Leafs. I know they're getting close to 200,000, but they haven't gotten there yet. And so some of the interesting things for me to look at in the future is, can anybody else develop a marketing buzz that attracts people to buy their vehicles? Because Colorado has this goal of basically 1 million electric vehicles by 2030. And to do that, I think we're going to have more than one manufacturer that people want to buy their cars. The other interesting thing is that typically new car sales, a third of the new car sales today are leases, and the average age of a car that's traded in on a new car is 6 years old. So that's much younger than the median that I see on the road in Denver. Will people, after they buy one battery electric vehicle, will they trade it in on another? Will there be a used battery or electric vehicle market? A lot of people don't buy new cars, they buy used cars. I'm not in the know on all of this, but my guess is the used electric vehicle market is kind of small right now. What's that going to look like in 2, 3, 4, 5 years? All of these things determine the how fast we move to electric vehicles and what percentage of the fleet they can be. And I'll end up my summary by saying the difficulty with reducing criteria pollutants is you've got to get a battery electric vehicle to replace a high emitter. And there are all kinds of difficulties involved in that. High emitters, the ones that are at the extremes of the distributions, that tail that I showed you in the distribution, the 300, the 400, the 500 gram cars, they have a socioeconomic difference than median cars. They have probably a racial difference than median cars. There are all kinds of differences. And by and large, right now, battery electric vehicles are being primarily sold to well-doing white people, to just sort of put it bluntly. And the question is, how do we get these cars to replace the cars that we need to be replaced? And it's potentially an intractable problem until we get the ability to have maybe an all-electric fleet. And I haven't even gotten into the discussion of reducing heavy-duty NOx emissions and electrifying that side of the equation. This is just the light-duty fleet. But even if we were to have 1 million electric vehicles by 2030, that's only about a fifth of the fleet. And if they're replacing the median car, there'll be very small reductions in criteria pollutants. Now, CO2 emissions, there will be significant reductions. But in terms of the ozone issue, we're talking about hydrocarbons and NOx. And they're not very large emission reductions that are available in a lot of these 2009 and newer cars, where a lot of these battery electric vehicles are ending up today. Finally, I will end with a slide. This is just a small sampling, but all of these references talk directly to either the databases I showed today, or the instrument, or the method, or a wide range of all the things that we've done. And like I said, if you go to the website, there's everything that we've done, and you can find, if there's something you're interested in, the ships or small boats or trains, aircraft, you can find those papers as well. And I'm going to stop there. I find my experience with the virtual meetings is that discussions is more difficult than it is in person. And so I wanted to leave enough time so that if we do have questions or we do want to discuss some other things, we can do that. So thank you for listening. And I'll shut up now and listen to you for a minute.
Thank you, Gary. Does anyone have a question they'd like to ask? Well, I'll go ahead and maybe start the conversation going. Gary, I was wondering, with your graphs as they are laid out, do you expect over time for those larger emitting or the greater emitting vehicles to eventually filter out in the process?
Well, what you'll notice is that even in 2020, they're at the extreme ends of the distribution, they're very high emitters. So there is an equilibrium that takes place in a fleet. There is some turnover rate and there is some breakage rate. What we've seen over the last 25 years is that the breakage rate is plummeted, but it's not zero. And so cars do break and they do become mal-maintained for various reasons. Um, uh, one of the classic reasons is kids street racing. Pick up any hot rod magazine if you can find a paper one. I guess probably now you got to go online. You can't just go to the grocery store and find one. But they used to advertise in the backs of those magazines how you can get an extra 200 or 300 horsepower out of your Honda Civic engine. And so kids modify these cars, adults modify cars and trucks. That oftentimes puts them into high emission categories. And so, no, they're not going to completely go away until we either A, make a car that never breaks, and they do pretty good at that, but I don't know that they'll ever get to that point, or we completely electrify the fleet. And what happens is they become a larger and larger fraction of the total emissions. I didn't mention this. You know, the top 1% for CO in 2020 in Denver, I want to say, accounts for 56% of the total emissions. And so they're just what's that? 20,000. There's 200 cars that are responsible for more than half the emissions.
Amazing. Detlef, do you want to go ahead and ask your question?
Yes, thank you very much. Gary, it was an excellent presentation. Thank you so much. When you classify these cars, you've mostly been doing this by age. I'm wondering if you have any insight, how much this is really driven by age versus, and you kind of touched this already, malfunctioning, modified exhaust systems, possibly modifications in violation of required emission controls. I wonder if the issue is more, it's not so much old cars, it's cars that have been modified and that are in violation with emission control systems. And I'm not sure if we have a system in place to capture these violated vehicles and pull those off the streets. But you know all this so much better, so I'm curious your opinion.
Cars do deteriorate, and they deteriorate on average, but it's very low levels. And I pulled up this slide, and I can pull up the other one. If you look at the very last black dot at, I think it's 25 years old, and the very first.
Gary, which slide are you on? I think I'm
on slide 15. I'm sorry.
Okay, I'm not. Thank you.
Oh, I'm sorry. I'm not in control anymore.
No, sorry.
All right, slide 15.
Okay, it's up now. Thank you.
Good. All right. So the 24-year-old car here is a 1996 model year. And the first blue triangle is a 1996 model year. Now, if you look very carefully, that black dot is a little bit higher after 24 years than it was when it was 0 years old, but it's not higher by a lot. Now, there's more going on here than just age, because there's also probably 98% less 1996 is measured in 2020 than there were in 1995. But cars break at any age, and it's not just an age thing, but on an average basis, you do see older cars having higher average emissions. I don't know if that addressed your question or not. And the question is, how do you remedy that problem? And of course, I've given up on remedying that problem because Don talked about this for his whole 30 years doing it, and I've talked about it. And basically, the solution has been we're always going to manufacture lower emitting new cars and hope the problem goes away. And what we've gotten into a situation now is like if you trade in a 10-year-old car today on a brand new one, you don't get any emissions benefit because that 10-year-old car on average has about the same emissions that that new one does. And so we've lost fleet turnover as a major driver in reducing on-road vehicle emissions. It just doesn't exist anymore. And that's the issue. That's the problem electric cars have. Until they replace large swaths of the fleet, and I'm talking 70, 80%, you're probably not going to see significant reductions in criteria pollutants. You will for CO2, but not for CO, hydrocarbons, and NOx.
Well, thanks for that. But there's one point of my question that I want to push you a little bit harder on. And now who's talking here is a bicyclist. I'm out there riding quite a bit on the streets, and I'm sometimes shocked what cars or trucks pass me and how dirty their emissions are. And they might not all be all that old. So the core of this question was, can you differentiate what portion of these high emitters are because they're just old versus emitters that have their emission controls removed or are malfunctioning that would never make it through an emissions test? I mean, I see.
Well, but they can rechip cars today, Detlef, and enhance performance. And if you go into your emissions test, all you do is have to put in the stock chip. There are scofflaws that are doing that. I almost put in a graph of who are the 99th percentiles. You see cars out on the road that have license plates that don't go with the car. You see cars out on the road that, for whatever reason, haven't had an emissions test in 3 years, but they're licensed. You see things along those lines. So yes, it does happen. And we do not have anything in place to deal with it. The IM program is very ineffective against people who purposefully modify their cars because they can purposefully remodify them. But no, I can't look at a car and tell you, other than the model year, whether I think it's actually really broken or it's been modified. Now, for diesels, if you see a 2009 and newer diesel vehicle and it smokes, then they've removed the DPF. That one you can tell. But a lot of these other ones you can't. Let's do another question.
John or Ginger?
This is John Jacobs. Thanks for the presentation, Gary. Very good. So I imagine you're familiar with revised anti-tampering policy or tampering policy that EPA put out December of last year for mobile, motor vehicles and equipment. Well, among the things they talk about are some 550,000.
You're talking about the diesel report. Yeah, I did see the diesel report.
And they've all removed their DEF diesel exhaust fluid, controls, and that's that newer than 2009 truck that smokes you're talking about.
Right.
So,
but by and large, I don't see that, John, in Denver and Tulsa.
Okay.
Not to the magnitude. Not to the magnitude that they insinuate in the report.
Right.
I've got another graph. I can send it to you. I didn't present it because we're talking about diesels. You know, by and large at 6th Avenue in 2020, 2016 and newer diesel trucks have the same emissions as gasoline pickups.
Okay.
They do go up quicker after that, but then you get into this issue where you're not quite sure what the certification standard is as you go back in time. And diesels have come down slower. NOx emissions in pickup trucks and gasoline engines went down really fast in the early 2000s. In diesels, it's taken a much longer time, but they have caught up.
Okay.
And I would think if they completely removed, if the numbers of trucks have completely removed their DEF systems as insinuated in that report, I would see that in spades, because I saw the Volkswagen cheating. If you're interested, there's a paper on the website where 3 months before Volkswagen admitted to cheating, we published the data showing that Volkswagen 2009 vehicles didn't have lower NOx emissions than the 2001s to 2005s that had no controls, and something funny was going on. Anyway, so
that's great. Anyway, thank you for your presentation and your response to my question, Gary.
Yeah.
Ginger, did you have a question?
Yeah, I was just wondering, so this fleet data is specifically like cars registered in Colorado, is that correct?
Well, for the Colorado sites, yes.
Okay. And so does the data account for vehicles from out of state, or does it just automatically exclude those?
In the data that I showed you today, they are excluded.
Okay.
I don't have a good way of processing registrations from out-of-state plates. I can tell you from the original data set how many of those plates there possibly are. Basically, I'll end up with 80% matching registration records for total attempts. And what I mean by total attempts is that when a car drives by and I attempt to measure it, I either do measure it or I don't measure it, but it's an attempted measurement. And so when we end up with the data sets and having them processed, I'll end up with about an 80% match rate, which if you look around, it's exceptional compared to, say, for example, what EnviroTest does with their local systems. They're closer to more like 50%.
Okay.
But no, it does not include out-of-state cars. I do have some data sets where I've included out-of-state vehicles. The Chicago 2020 data set that's on the website, because of COVID and the traffic was down and things like that, I actually went through and looked up all the out-of-state plates I could find by hand. And you know what I found was that in Chicago, the out-of-state plates had similar emissions patterns to what the in-state plates look like. And part of that's because of the large numbers in terms of the in-state plates. These distributions and these graphs that I showed you today would look almost exactly the same, whether I showed you data from LA, Chicago, or Tulsa, Oklahoma. And by the way, Tulsa, Oklahoma doesn't have an IM program, but they look the same. And so the distributions that we see in Denver are the same distributions we see everywhere else. Now, there'll be small tweaks because, for example, Chicago tends to be about a year and a half younger from a fleet standpoint than Denver or Tulsa. And Chicago doesn't have as many pickup trucks as we see in Denver and Tulsa and things like that. So there are differences, but by and large, the statistics will hold across the country.
Okay, that's interesting because, yeah, I was just wondering like what kind of impact out-of-state vehicles might have. I used to live in Tulsa, and so I just kind of wondered anecdotally if there would be like more modified trucks.
You and I both know when people move here, they don't re-register their car until the plate runs out.
Yeah. Yeah.
Even though it's against the law, but you know, how do you enforce that?
Right.
So is there another question? We're getting close to the end of time. I don't want to go over.
One more from Detlef. Go
Go,
ahead.
Detlef.
Maybe, this a quick one. So when you measure, a vehicle that's ways above, that tail end, super high emissions, does that trigger anything? Does that go anywhere? Is anybody trying to find?
No, this is all research, Detlef. In fact, I'm sometimes reluctant to name names when I publish stuff. So like that Volkswagen article that I told you about, we didn't name Volkswagen. We just named the engine, that it was a 2-liter diesel engine, and they were the only ones at the time making it. But no, it doesn't go anywhere. And neither does any of the clean screen data that CDPHE collects in Denver. They may use some of the high emitters in a study project, or they may use them for analysis. But there are no penalties for driving a high emitting car in Denver.
Okay.
I can't resist this. I have to tell people the clean screen program in Denver, I tell people, is the quintessential government program because it costs boatloads of money. The public loves it, and it does absolutely nothing to clean the air.
Well, we'll try to pass that on to our city leaders. Yes. Thank you, Gary.
You're welcome.
Very interesting talk. Thank you, everybody, for attending. And we just want to let everyone know that our Rocky Mountain State Section Air Quality Conference has been postponed, and we are having it now in October of 2021. And we are currently accepting abstracts if anyone wants to present at that conference. But thank you all for attending, and we hope to see you at the next luncheon.
Thanks, Mary.
Thanks. Thanks, Gary.